Hey everyone. So now we're moving on to continuous random variables. And remember, in contrast to discrete random variables, where we had a countable number of events and we could compute probabilities for each individual event or each individual outcome of the random variable, when we move to continuous random variables, we have an infinite number of possible outcomes of that random variable. And therefore, we cannot directly compute the probability of a specific event, but rather we, if anything, compute the probability of a range of events, right? And think about this example of computing the probability of you're waiting at the bus stop and you're trying to trying to calculate the probability of the bus arriving 5 minutes from now. If you kind of try to compute that probability down to the millisecond, that probability is essentially zero because there are an infinite number of possible times where the bus could arrive. But rather, instead of thinking about a specific time down to the millisecond, we would think of the bus arriving between 9:05 and 9:06, and that probability can then be computed based on the probability density function, right? Um, the simplest form of a continuous random variable is a uniform distribution. A uniform distribution describes a probability distribution where every value within a given interval between a and b has an equal likelihood, right? So any time is equally likely. The bus would, if you're waiting at the bus stop, the bus would be equally likely to arrive at any time from now, from immediately to 10 minutes from now, for example, right? So what is the probability density function of such a uniform random variable within the interval a and b? It can be described as follows. The probability density function is 1 divided by b minus a, if a is within the interval, so if a is smaller or equal, if x is smaller or equal to a, or if x is larger or equal to a, and smaller or equal to b. So as long as x is between the interval a and b, the density is equal to 1 divided by b minus a. Why is it 1 divided by b minus a? Well, this is the entire sample space, and if you look at the integral of or the area under the curve, under this kind of uniform distribution across the range from a to b, then then the integral of this uniform distribution with the value 1 divided by b minus a just turns out to be equal to 1, right? So that's the ultimately the result that we want to, or based on the probability axioms, where all the probabilities ultimately have to kind of sum up, or all the probabilities in the sampling space have to be equal to 1. That is basically satisfied if each individual probability or each individual density, since this is continuous, we're not really talking about individual probabilities, but rather the densities across all ranges of x have to be equal to 1 divided by b minus a, okay? And of course it's 0 otherwise, right? Everything outside of that interval is basically outside of the sampling space. All right. Then, based on the probability density function, we can compute the cumulative distribution function, which is, of course, 0 if x is smaller than a. It's x minus 1 divided by b minus a for x between a and b, and 1 if x is larger or equal to b, right? And we can compute this by taking the integral of this up to the point x, and you'll see that then that basically is a steady increase from 0 to 1 as soon as x is larger or equal to b, okay? We can also compute the expected value, which is just a plus b divided by 2. So, kind of think about this going back to this example of waiting at the bus stop. The bus, the interval might be between 0 and 10, right? and it's a uniform distribution, then the average wait time would be 5 minutes, right? So that's 10 plus 0 divided by 2, and that's 5, okay? The variance of a uniform distribution is equal to 1 over 12 times b minus a squared, and again we can get at that by kind of plugging in our definition of the variance of that random variable. Okay. All right. Wait a second. Okay. Next, after talking about the uniform distribution, where each outcome basically has an equal likelihood, we're going to talk about the normal distribution, which is also referred to as the Gaussian distribution. And it's one of the most important distributions in statistics because, as we will kind of explore in more detail later on, the sum of many random variables from the same distribution tends to follow the normal distribution, even when the original distribution is not normal, right? And that's why we're gonna talk a lot more about the normal distribution, especially when we reach the central limit theorem. Ultimately, the normal distribution, as I said, it's a continuous random variable, and it can take any number on the real line from minus infinity to plus infinity. The probability density function looks a little bit more complicated, but it's important to kind of remember it and recognize it. It's 1 divided by a square root of 2 pi times sigma times e to the power of x minus mu, so that's the deviation from the mean squared, divided by 2 sigma squared, okay? And the cumulative distribution function is, of course, since this is a continuous random variable, is of course equal to the integral of this density function up to the point x. And the important or the tricky thing here is that this doesn't have a clear closed solution. It's not easy to compute this integral. So ultimately, what you have to do in cases like that is to use normal distribution tables to look up the values of the cumulative distribution function, or directly compute it in R. It's not you cannot analytically solve this integral. But the important thing, even though this formula looks incredibly potentially intimidating or potentially complicated, it is really important, because a lot of the basic theories of statistical inference and our kind of our basic strategy to quantify uncertainty around our estimates are based on large sample theories, particularly the central limit theorem. And even though the underlying PDF and CDF look rather complicated, there are two important things that are quite easy, or quite easy to remember. The expectation of x in this case, so the expected value of this normal distribution of this form is equal to mu, and the variance of this normal distribution of this form is equal to sigma squared. Okay. Let's see. So in other words, in notation, what we often see is we're talking about a normal distribution with mean, mu, and standard deviation sigma, and the way we write this, or the way you kind of see this in stats books often, is x is distributed as a normal distribution with mean, mu, and variance sigma squared. Okay, so this notation describes a normal distribution that has a mean of mu, a variance of sigma squared, and follows a normal distribution according this probability density function that I outline here. We often also see what is called a standard normal distribution. A standard normal distribution is a normal distribution with a mean of 0 and a variance of 1. Okay, so just to give you a better kind of idea of what these normal distributions look like with varying means and varying standard deviations, here I have I just plotted the probability density function and the cumulative distribution function with varying values for mu and sigma squared. The standard normal distribution is the black line up here, and of course it is centered around 0. It's symmetric, and we see that most of the probability mass is between -2 and +2 standard deviations from 0. If the standard deviation is equal to 2, this bell curve is wider, as we can see here, and most of the probability mass is around -4 and 4. If we have a smaller standard deviation, of course, the bell curve is more narrow. And if we have a mean of 1, for example, this bell curve is centered around the average of 1 and more narrow than the standard normal distribution. Okay. Remember always the cumulative distribution function is basically the area under this probability density function up to a given point. So in that sense, it is always increasing, it's steadily increasing or continuously increasing for the probability for the standard normal distribution. Here, the black line, we see how it approaches. It is 50 or 0.5 for x being equal to 0, and approaches 1. If we have a larger standard deviation, this cumulative distribution function is ultimately a little bit less steep, which is kind of following if you kind of think about the underlying area under this curve, under the density function up to that point, you'll see how this leads to a higher cumulative distribution function for lower values of x, and ultimately a lower probability or cumulative distribution function for higher values of x compared to the standard normal distribution. And then if we have a mean of 1 and a standard deviation of 0.5, again, the cumulative distribution function is steeper, and it is shifted to the right, so that at x equals 1, we have the probability of 0.5. Okay. There are a couple of important properties of the normal distribution that I'm just going to mention briefly. Suppose we have a random variable x that is distributed normally with a mean of mu and a variance of sigma squared. Then we can specify a new random variable z, which is just the random variable x plus a constant c. If that is the case, then we know that z is also normally distributed with a mean of mu plus c and sigma squared. The variance is the same, right? So adding a constant to a random variable still results in a random variable. The only thing that changes is that the mean is shifted according to that constant. Similarly, if we multiply a normally distributed random variable by a constant c, the resulting random variable is still normally distributed. The mean is again changed, we have to kind of take into account the mean, which is again multiplied by this constant c, but it's now not only the mean that changes, also the variance changes. The variance is now c times sigma squared. Or we could, multiply this out, c squared sigma squared, okay? And ultimately, these properties imply that the z-score of a normal random variable that we talked about in the past, kind of standardizing a random variable, follows a standard normal distribution with a mean of 0 and a standard deviation of 1. And so the z-score, just to reiterate, is implies taking our random variable, subtracting the expectation of that random variable, and then dividing by the square root of the variance, so the standard deviation. And that z-score then is distributed according to a normal distribution with mean 0 and standard deviation of 1. Right? And I should have mentioned this earlier. I included a couple of awesome visualizations on Canvas that are linked, where you can kind of go through this z-score standardization and kind of visualize this for different types of distributions or for different values of mu and sigma squared, and kind of see how the standardization returns any type of distribution back to the standard normal distribution. So go check out those visualizations that are linked, and make sure to look at that additional material as well. All right. The other important property of normal distributions is related to two random variables that are distributed normally. Suppose we have x and y distributed as normal distributions with separate means and standard deviations, and then we look at the distribution of a third random variable z that is just the sum of those two random variables, each multiplied by a constant a and b. Okay. The sum of these two normally distributed random variables is also normally distributed, with the expectation now being equal to the sum of the expectations. Okay, so basically this rule implies that if we have two random variables and we take the sum of those random variables, then the result is still normally distributed with an appropriate mean according to the rules that we described earlier. Okay. Similarly, we have the variance of this z, and now it is important to recognize that since these two, the random variables x and y, are in this scenario assumed to be independent, right? So since they're assumed to be independent, the variance of their sum is the sum of the variances, and we take into account the constant, or the multiplication by the constant, by pulling it outside of the variances, and what we're left with is a square variance of x plus b square variance of y. Okay. More generally, if we have I independent variables, now denoted as xi, which are independently distributed as normal with with the same expectation and variance, then the sum of those independent variables is again normally distributed, where the mean is equal to n times the expectation of x, and the variance is equal to n times the variance of x. Okay. Lastly, another important property of the normal distribution, which we will refer to later on when we kind of talk about confidence intervals and so on, is if the data are distributed according to the normal distribution, about two-thirds of the probability mass are within one standard deviation from the mean, and approximately 95% are within two standard deviations from the mean, right? And we can show this by considering the probability that a random variable with mean mu and standard deviation of sigma lies within k standard deviations from the mean for a positive constant k larger than 0, right? So in order to simplify this, we can consider the z-scores, or basically we can look at this statement, the probability of x being equal to, or being in the range between minus k times sigma, or mu minus k times sigma, and mu plus k times sigma. This is basically just the statement of the random variable with mean mu and standard deviation sigma lies within k standard deviations from the mean. This is basically kind of formalizing that statement. We can then rearrange this a little bit by subtracting the mu on each in each part of that equation to kind of leave it here in the center, and then divide by sigma, and so we are left with the probability of minus k smaller or equal to x minus mu divided by sigma smaller or equal to k. And note that this is now the standardized z-score, which we know that it's distributed according to a standard normal distribution with mean 0 and standard deviation 1. And that means the probability of being within minus k to k standard deviations from the mean is equal to the cumulative distribution at k minus the cumulative distribution at minus k. And we can directly plug this in for our standard normal distribution. Now we're using the p prefix for the normal distribution, and we see that 68% of the probability mass is within one standard deviation, and 95% of the probability mass is within two standard deviations from the mean, right? So if we have a random, if we have a normally distributed random variable, we know that 95% of the probability mass is within -2 and 2 standard deviations from that mean. Okay. All right. And this we'll get back to this kind of fact about normal distributions and the probability mass of normal distributions being within 2 standard deviations when we get back to confidence intervals and hypothesis tests and kind of significance levels, essentially. Okay. Lastly, I want to briefly kind of bring this back to kind of an applied example why these distribution functions are helpful and useful and help us understand specific phenomena. And one phenomena in the book that was discussed in the introduction of a regression was this idea of regression towards the mean. And we can now kind of revisit this problem from the book using our understanding of the normal distribution, right? So suppose we're looking at an example where we look at the relationship between students' final exam score as a function of the average problem set score for the same student, right? So we observe, so for example, in this class, we observe problem set scores for all students, and we basically examine the relationship between the problem set score and the final exam score. And suppose this relationship in the population can be described as follows. We have an intercept of 15, and every 1 unit increase in the problem set score is associated with an average increase in the final score of 0.8, and we have an error term epsilon. And now suppose that this error term follows a normal distribution with mean 0 and a standard deviation of 5, or variance of 25. The question now, and this is kind of core to this regression to the mean idea, suppose there are two groups of students. One group that scored around 60 on average on the problem sets, and one that scored around 80 in the problem sets. And now the question is, which group is likely to do better in the final than they did in the problem sets? Okay. Ultimately, the answer, or in order to answer this question, we have to look at we have to compare two different probabilities. One is the probability of y1 being larger than 60, conditional on x1 being equal to 60, right? So that's the first group of students who received a score of 60 in the problem sets. What is the probability that these students receive at least a score of 60 in the final exam? And we have the probability of y2 being larger than 80, conditional on x2 being equal to 80, right? So conditional on having scored 80 in the problem sets, what is the probability of doing better than 80 in the final exam, right? And so intuitively one might expect, okay, they both, they're both equally likely to do just as well in the problem set as they will be doing in the exam. So this shouldn't really differ, but this phenomenon of regression towards the mean ultimately tells us that this is not the case, right? And we can show now mathematically why this is not the case, right? In order to answer this, let's first look at the probability of y1 being larger than 60, conditional on x1 being equal to 60. So how do we do this? The first thing we have to do is we have to plug in our x1 value into our linear regression model, which we just assume we know as the population model. And that is equal to 60 times 0.8 plus 15, and that is equal to 63. So y1 conditional on x1 being equal to 60 is equal to 63 plus a random error that is normally distributed with mean 0 and standard deviation of 5. Okay, and so the distribution of that, since we have a constant and a normal distribution, that sum is of course normally distributed, so y1 conditional on x1 being equal to 60 follows a normal distribution with mean 63 and standard deviation of 5. Okay, so what is the probability of y1 being larger than 60 conditional on x1 being equal to 60? That is just the probability of y1 minus 63 divided, so this is basically now z-scoring, subtracting the mean and dividing by the standard deviation, and then and then looking at those probabilities, and we can directly do this in R using p norm for the standard normal distribution, since we standardized this score. So 60 minus 63 divided by 5, and the probability of that is 0.72. So the probability for students who scored 60 on the problem sets, the probability of them doing at least as well or better in the final exam is 72%. Okay. Rather than z-scoring in R, we could also use the pnorm command slightly differently, where we basically just look at the probability of observing smaller or equal to, a value of larger or equal to 60 of a normal distribution that has a mean of 63 and a standard deviation of 5. The argument here, lower tail equals false, implies that we're looking basically at the inverse rather than looking at values being equal or smaller to 60. We're looking at values of larger or values larger or larger than 60. Okay, so that means we're not looking at the lower tail, we're looking at the upper tail of the distribution. Okay, and that is the same result. I didn't print it here, but if you run this command, you'll get the same result, right? So rather than standardizing and looking at the probabilities in the standard normal distribution, we can also in R specify the varying mean and standard deviation and directly plug in 60 as our value. Right. So now we can do the same thing for our second set of students, which scored 80. So here x2 is equal to 80. If we plug this in, we see that y2 conditional on x2 being equal to 80 is again distributed normally with a mean of 79 and a standard deviation of 5. If we look this up in the normal distribution, or if we z-standardize or compute the z-scores by subtracting the mean and dividing by the standard deviation, and then looking at the probability of observing a value 80 that is equal to 80 or larger, then we see the probability here is 0.42. So the probability for students who scored 80 to do at least as well in the final exam is substantially lower at 42%. Okay, so that's just one example where we kind of now, by kind of invoking or kind of making an assumption about the error term in this linear regression model, we can kind of explain or get a better understanding of why we observe this phenomenon of regression towards the mean by showing that the conditional distribution given the underlying linear regression model implies that the probability, the conditional probability for high scoring students previously to score at least as high as they did previously is lower than for lower scoring students. All right, in the next video, I'm going to talk about large sample theorems to conclude our discussion of probability.